right, welcome back everyone. In the next part of the lecture, we are going to start talking about how to establish a trig identity. And the idea is pretty simple. Basically, we pick one side of the equation to work with, and then we transform that side using the identities that we already know, Pythagorean identities, even odd identities, etc. And we keep simplifying the one side until we can transform it into the other side. That's sort of the key here. Now, this is a little bit different than solving an equation. When I give you something like x plus 2 equals 7 and I ask you to solve it, then it's totally fine for you to move things from one side of the equation to the other because we're trying to find out what value of x makes the left side equal to the right side. But that's not what we're doing with a trig identity. We're not trying to find a value that makes the left side equal to the right side. We're trying to show that the left side is always equal to the right side. And so we do that by taking one side of the equation and transforming it and transforming it and transforming it until we can show that it's equal to the other side of the equation. So I won't be moving things from left side to the right side. I'll be starting with one side of the equation and manipulating just that one side until I can turn it into the other side. Now, as far as which side to work with, the usual idea is to go with the more complicated looking side, and that's because it gives you more options of things to do. And we're going to see that right away with the first example. Here I've got an identity to work with, and if you're looking on the left side, there's lots of things you could do. Cotangent could be turned into cosine over sine. Cosine squared, you could use a Pythagorean identity and turn that into a sine squared if you wanted to. You've got sine of negative theta. You could use an even odd identity. On the right side, there's less obvious things that you could do. I mean, you could turn cosecant into 1 over sine, but then I'm not sure really what else you would do after that. So here, that's my plan. I'm going to start with the left side. And on my left side, I have sine of negative theta, cotangent squared, cosine squared, cotangent squared theta over cosine squared theta. And first thing that I'm going to do is look at that sine of negative theta and say to myself, well, I'm going to apply my even odd properties. Sine is an odd function, so sine of negative theta is negative sine of theta. Okay. Now, the next thing that I'm going to do, I'm looking at that cotangent squared theta, and I know that cotangent is cosine over sine, so that's my next plan. Why don't I rewrite things as cosines and sines? So cotangent squared is cosine squared theta over sine squared theta. It's always good to take a pause and look back at where you're started and where you're planning to get to. And so where I'm planning to get to, I'm trying to show that this is equal to the right-hand side. I'm trying to get to negative cosecant theta. And you'll notice there's no denominator there. And right now I've got something that has a denominator. So I guess my plan is, and in fact, it's a complex fraction because there's a fraction inside of a fraction. I'm going to start to simplify things a little bit. And my plan here is that I've got the numerator divided by cosine squared, which is the same thing as the numerator divided by cosine squared over 1, which I'll flip and multiply. So in other words, I will have the numerator multiplied by 1 over cosine squared. So we'll have that this is now negative sine of theta times cosine squared theta over sine squared theta. I'm going to just zoom in and make that a little bit nicer looking. And then I said divide by cosine squared theta is the same thing as divide by cosine squared over 1, which is the same thing as multiplying by 1 over cosine squared theta. And then now we're kind of on the way because I can see there's a bunch of things that are going to cancel. I have cosine squared and cosine squared will cancel, and I have the sine in the numerator with the sine in the denominator that will cancel. So what am I left with? I have a negative, and I've got a single sign in the denominator. So what I have is that I've got negative 1 over sine of theta. Now I'm actually a lot closer to where I need to be, because looking back at the beginning, we're trying to show that the left side is equal to negative cosecant theta. We have a negative, and 1 over sine theta, oh wait, that is cosecant theta, so actually we are done. We showed with a sequence of steps that you're able to take the left side, one side of it, and show that it's equal to the right side, that the left side is always equal to the right side. And so therefore my identity has been established. You now can say that the original thing that we were looking to show, that this is always a true statement. So sine of negative theta cotangent squared theta over cosine squared theta, that's always equal to negative cosecant theta. All right, let's do another one. Here we've got 3 sine squared theta plus 4 cos squared theta equal to 3 plus cos squared theta. And you've got lots of options. One option that doesn't exist, if you're planning on moving the cos squareds from one side of the equation to the other, resist that urge, because of course we're not trying to solve an equation, so we're not moving things from one side to the other. We're showing that one side of the equation can be transformed and turned into the other side. And so here, actually, both sides seem like a reasonable choice for me to work with, because I'm looking and I see sine squareds and I see cosine squareds. And so my little note that I'm making to myself here, of course, is if you're thinking about your Pythagorean identities, then good for you, because it's exactly what you should be thinking about here. We know that sine squared plus cosine squared is equal to 1. And so that means you could replace cosine squared with 1 minus sine squared. You could replace sine squared with 1 minus cosine squared. Now, this is my plan here. I'm going to work with my left side, which is 3 sine squared theta plus 4 cosine squared theta. And I'm trying to turn it into 3 plus cosine squared theta. So basically my idea here is I know that I need to get rid of that sine squared theta. I need that to be gone, because the right side doesn't have any sines in it whatsoever, just cosines and numbers by themselves. So I'm going to use the fact that I know that sine squared theta is the same thing as 1 minus cosine squared theta, and that's just from taking a Pythagorean identity and rearranging it. So instead of having 3 times sine squared theta, I'll have 3 times 1 minus cosine squared theta. And then at that point, it's pretty much finished, because I just need to now expand 3 times 1, 3 times cosine squared, and then I could combine together the cosine squareds, negative 3 cosine squared plus 4 cosine squared, that's the same thing as 1 cosine squared. So we're having 3 plus 1 cosine squared theta. Oh, okay, great. So that is the right side. So now we've shown that the left side is equal to the right side. We've established our identity. Now, that's one way you could do it. I mean, I want to show another way that you could do the same sort of a thing. And so here, I'm going to do the left side again, but I'm going to do something different, which is on my left side, we had, so I'll say or, we could start with the left side, which was 3 sine squared theta plus 4 cos squared theta. And I'm going to rewrite this. The 3 sine squared theta I'll leave alone. The 4 cos squared theta, I'll split that up into 3 cos squareds plus 1 more cos squared. And the reason I did that is because I know that I could then factor 3 out. From the first two terms. And then I have something very nice. I have inside the brackets sine squared plus cos squared, which of course we know is equal to 1. That's our old friend, the Pythagorean identity, coming back to haunt us. So really what we have is 3 times 1, which is just 3, plus that remaining cosine squared theta. So again, left side is equal to the right side. So this is something that's kind of a nice thing about establishing trig identities. There's not just one correct way to go from beginning to end, or only one possible sequence of steps that you could work through. So you could see that one option that I worked with here was replacing the sine squareds with 1 minus cos squareds. The other idea that I had here was trying to get a cos squared plus a sine squared with the same coefficient in the front so that I could factor that coefficient out and use my Pythagorean identity. Either way, as long as we're using identities that we already have established, Pythagorean identities, even odd identities, etc., and doing valid algebraic steps, as long as, again, we're not inventing our own versions of algebra, then what we're doing should arrive at the same end point. Okay, we'll take a pause here, and then we're going to come back and do a few more examples.